Hi, welcome to the sixth video on Introduction to Statistics from Neural Network. So in this video, we will solve our governing equation is this one. So this is a one-dimensional transient heat equation. So we'll be solving over the domain 0 to 1 over some time. So we have chosen, so as usual, we will approximate the solution using neural network. So we know U is the solution that will be approximated using neural network, which having three parameters, weights and bias. So we have three losses. One is loss due to partial differential equation. Another one is loss due to initial condition. Another one is loss due to boundary condition. We will minimize the total loss. Here U theta is approximation, neural network approximation. So when we substitute this neural network in the similarly, we'll be having initial condition loss and boundary condition loss. So the neural network should also satisfy the initial condition and boundary condition. Then we will calculate the total loss. Then we will minimize the total loss through some optimization algorithms. So in this video, we will explore another activation function that's a parametric optimization function. That's a parametric transaction. So it's an adaptive activation function. We also test the sensitivity of the initial condition to the neural network because pains are based on optimization algorithm. Optimization algorithms are very sensitive to the initial condition. For example, let's say we are using the gradient based method and we have a curve like this. If our initial guess is here, it will come to this minimum. If our initial condition is here, this will come to this minimum. So initial condition also plays a big role when we use gradient based optimization algorithm. So if Adams and some of the momentum this optimization algorithm may escape from local minima, but those are not guaranteed because they are still a local optimization. So now we shall get into before that we shall see other effects. So here we will consider several activation function, sorry, initialization algorithms, the saviors uniform and saviors normal. So these are initial conditions. These initial conditions are good for things. Of course, we cannot claim this always work for all the problem. So in this test case, we will test. So when I was testing, the default was better than the Savior's base initial condition. So as a thumb rule, or in most of the cases, Savior's initial condition works for things. Another one is camming uniform and normal. This is very good for page browsing or ReLU when we use a ReLU activation function. But these are not good for neural network because, sorry, pins. Because in pins we may calculate the second gradient. So at that time, the ReLU activation becoming a constant value or 0. So when we go for higher derivatives. So in this video, we will see how to call different initialization. Maybe if you want some tutorial on how to make our own initialization process, please drop one comment. I shall make it. So in this video, we will see how to make it. So here we will be using the parametric target, but in this thing, we'll be having an extra parameter alpha. So that we will feed us. So for this problem, this is the analytical solution. So we shall get into the code. So you can find this code in the comment. So this is a good practice because this will ensure so we have the same solution when we run different times. For example, if we don't set it here, PyTorch follows or PyTorch standard initialization always go with the random values. So every time we may not get the same results. So now we shall see how to define a parametric downledge. So here we are defining that's a class. So name of the class is parametric downledge. So that this is a subclass of NN modules. The last video these are NN modules is a parent class where we have all the functions and definitions of how to define a neural network, like activation functions, linear basis, sequential, those informations. So it is if we define that NN dot parameter, and if inside that we are pausing some value. So here we are pausing a value initial alpha. So that's a variable. In the next step, we will make it 1 or 0.9 based on our requirement. It will take a data type float32 because most of the neural network use float32 as a default basis. But in most of the computation, we prefer double, that is float64. So here we have taken turnH, and the turnH takes the argument alpha. Self.alpha is a variable that we have designed, I mean learnable variable, and it is a standard input to the activation function. So here we have two. We will be testing two. So this set will make a several layer of neurons. So that will be getting multi-layer. So this is just a easy way of. So in this tutorial, we also test the effect of the initialization. So this is a forward model, a forward neural network model. So what we are doing is here we already make a sweep stack of layer where we are. So as usual, we know x and t are the independent variable of this partial differential equation. With respect to those variable, we will be calculating gradient. That's why we are ensuring the x dot requires gradient is true through these commands. So then this is the instance of the class. So we already defined a model which takes x comma t as a input. This is a neural network model. So first we will calculate the first derivative with respect to time. Then we also calculate the first derivative with respect to space. So anyway, our partial differential equation does not have that first derivative of here. But to calculate u double s, we need that. That's why we are calculating exs. Then we will feed this as a input to this function. This function calculate the derivative of ux with respect to x. So name of the function is torch.autograd.grad. So it will take that first variable. For example, let's say we want to calculate derivative of ux. So we would be pausing the dependent variable here, and we are calculating this with derivative of this with respect to x. That means d of du divided by dx. So other things we should pause are the size of that. The gradient size should be same as u. Then we should specify the device. If we have a GPU, that is very good because GPU makes a job, makes our calculation much more faster than CPU. Finally, we are defining our PDE here for just UT minus alpha into EXs. So here we have defined that this quotient of dissipation as 0.01. This command ensure the PyTorch will go to CUDA, that is GPU if we have a CUDA, else or if we have a CUDA install, GPU and a CUDA installed. If that is not there, it will take CPU. So anyway, the simulation is over. We got a mean square error SPO of 1 to 10 power minus. This is how that error reduces. So you can notice that amplitude of the signal is reducing over the time because of because of physical dissipation. Now we shall change that or try the effect of initial condition on this problem. So maybe we shall make it a little simple. We shall go with 5 neurons and 2 hidden layers. We should start with atoms using Turner-Chalfant function. Let's solve this problem. So in this problem, I am unable to find any advantage of neural network over traditional numerical methods in terms of accuracy or computational cost or any stuff. Like, oh, this is a well-beaten problem by numerical methods. And we may have some advantage if we go for higher dimension. So higher dimension is a little bit hypothetical because heat equation we have at most we'll be having one time and one space, sorry, three space. That is t comma x comma y comma z. So that's the maximum dimension possible for heat. So if we have some hypothetical equation where we have n dimensions instead of x, y, z, we may have other dimensions like u, v, w. So in that case, numerical methods have some issue because of cost of dimension. So when we have these kind of issues, physics probably network may outperform traditional numerical methods. That's one of the advantages of physics informed neural network over traditional numerical methods. Another one of the biggest demerits of physics informed neural network over the traditional method is we already saw the convergence graph is a little bit saturated when we use optimization algorithm. Initially, it was good. Over the time, it's saturated. But most of the numerical methods can give you a good convergence. So if you use higher order methods, we make it even sharp convergence. But numerical methods also this optimization algorithm cannot show similar convergence. So they saturated of having 10 power minus 3, minus 5, minus 6, and minus 7. So that's one of the limitation. We can't really get real accurate results. So because of that, it's quite difficult to make any advantage when we use physics from neural network on these kind of problems. So these set of problems include heat equations, then Poisson equation, Laplace equations. So similar kind of elliptic equations. But in upcoming videos, when we solve some hyperbolic equations, we shall see some advantage. So in the last video, when we solve linear convection equation, we observe some advantage. And maybe once we completed all these basic equations like heat equations, Burgers equations, Navier-Stokes equations, and Euler equation, we shall see what are the cases where physics from neural network may have some advantage over traditional methods. What are the cases where numerical methods will have some advantage over traditional methods? And now we shall come to our discussion. So we have, in this case, we have simulated for Turnage activation function with the Adams optimizer. So we got some reasonably okay convergence curve. Let's see the solution. Solution is not that much good. When we run the parametric John Hatch, we got even better result. So it has even better convergence. Anyway, the solution is not that much good when we run for higher epochs and more number of neurons, but it's still better than when we use a Turnage activation function. So now we shall move to the or when we use SGDs, error conversion is not good, which is saturated after maybe it's almost saturated after 200 epochs. Solution is very poor. So optimization algorithms also play a good big role in the accuracy of the neural network or SAC for neural. So please always have an eye what optimizer you're using. Generally, it's good to use Adam optimizer followed by LBFGS optimizer. If you're still facing some issues, you can also go for second order optimizers. Now we shall see the effect of the initial condition on this problem. So now we shall change that to Adams. So we already saw Savior initialization is always good. So we shall test it. So when we use Savior initialization, the solution is not that much good when compared to the standard initialization. You can see the error is around 10 power minus 2. Loss is around 10 power minus 2. But when we use a turn H activation, turn parameter turn H uh, with the default initialization, we got a better solution. Of course, this solution is not good. So we cannot blindly say Saviour's initialization always works well. Now we shall go to Canon initialization. So what I have observed is even Canon initialization also not good for this problem. So default was better than any other initialization what we have tried here. Of course, it's also depends on number of neurons and layers that we. So please don't uh, completely blind on some initialization or optimizer. Some optimizer may work for other problems, some optimizer may not work for other problems. So it's always good to try all these variables if we are facing some convergence issue or we are unable to get a residual. So that's why I call physical neural network any neural network is more or like odds than the science because it requires a lot of skills than knowledge. It's very difficult to predefine or we, we cannot simply say this will always work. So we can notice the solution is bad. So you can play with different neurons, layers, learning rate uh, on this program so that you can come with some hypothesis or some understand. You may get a better understanding. Another important parameter we should get when we use deep learning is this learning rate. Better we shall go with the best configuration what we got. So let's say so learning rate also plays an important role. I already have one video how the learning rate affect the solution. For example, if we go for higher learning rate, we may get some oscillation in the solution. It's always good to go with low learning rate, then you can slightly increase the learning rate. Because if we go for very low learning rate, for this learning rate is just how much leap we should give every epoch. So we may not, it may take a very long time to reach the global minimum or local minimum. In this case, it got a better result when we use the learning rate 0.1. It's better than when we use 1 into equal minus 3. That's very interesting. Now we shall change the learning rate to maybe 2. Then we shall run the model. So when we increase the learning rate, model will have some issues because very high learning rate creates some convergence issue. So let's say we have a convex curve like this. If we have a high learning rate, so sometimes it may go here, again it will go here, again it will bounce like that. So that's one of the problems when we use a high learning rate. So it's always good to use a very low learning rate. If you want to see one animation how the learning rate affects the solution, I already have a video on that. I will put that video in the comments so that you can get a visualize how the learning rate affect them or optimization algorithm solutions. So this is very competitive one solution. I hope you enjoyed the today's videos. If you have any suggestions or any doubts or something, please drop in the comment. So the next video we shall again go to some hyperbolic equation. We shall solve a Burgos equation. Thank you for watching.